In this video lecture, we will study about buoyancy. Okay, so to recap, like so far we have studied about solids. We have talked about thrust, we talked about pressure, we talked about gravitation force, but we only discussed examples of solids, right? Hard object. What about liquids, or gases? So fluids in general, fluids are like both liquids and gases, right? So don't they apply thrust on the surface? Don't liquid apply pressure on the surface? Okay, now when we talked about thrust, right, we took an example of an object placed on the tabletop, and based on the weight of the object, it was applying thrust on the sample surface, right, on the direction perpendicular to the surface. Don't the liquid have the weight? So if I have a surface and I have some liquid on top of it, don't you think it is applying the force on the surface? Let's say another example, I have the surface here and I have a hollow container filled with liquid. Now don't you think that liquid is applying the pressure on the surface? Liquid have weight, right? They are applying the force and pressure too, similar to solids. And that we will try to understand more deeper in this topic of buoyancy. Okay, let me explain this, again, as I do generally. Let me explain this by giving you some kind of example from your daily activity or the experience you might have in your early years. So consider that you have a well which is filled with water, right? And let's say this is your ground level. Okay, so the person is standing somewhere here. Okay, and this is your pulley system. I'm gonna use it right here, pulley system, and then the string is going over the pulley, and then you are having a bucket which is filled with water. Okay, and then you're lifting the bucket. Now, don't you guys have experienced while the bucket is inside the water, it's easy to pull up, right? Means as long as the bucket is inside the water, you don't really feel any weight of pulling the bucket upwards. Let's say the bucket has reached somewhere here, even though it is only half immersed in the water, even then you will find that it's easier to pull it up. But the moment the bucket is like somewhere up above the surface, now as you are pulling the bucket up, it becomes very heavy, right? I believe most of you guys have experienced this or something like that of that sort. But the question is, why is that? What is causing that bucket to get heavier or lighter? The mass of the bucket is not changing because it is filled with water. Here it is filled with water, completely filled with water here, completely filled with water here. So the mass of the bucket is not changing, right? But what is causing the bucket to become heavy and lighter? Okay. Another example would be when you do the swimming, you feel light, your body is light, you can easily swim. But the moment you get out of swimming pool, you feel your body becomes heavy. Now, what is the reason for that? Another very drastic example would be, when you throw a stone in the sea or in the river, the stone sink. Like, so if this is a stone in the river and you throw a stone, it goes right inside the river, right? But you have seen many times the ships, they're easily going in the sea, and they are much more heavier than the stone. I was looking it up, but the Titanic ship, which is very famous, was about 52,000 tons. That's like much more heavier than the stone you are throwing in the river. But the ships are not sinking, but why the stone is sinking? So what is that particular property which is affecting all this behavior we are seeing here? What governs when something sinks, something does not? Which specific physics principle is guiding all this observation we are looking at? So, and that is exactly the buoyancy. All of this is because of buoyancy, and we will try to understand this more in this particular topic. So let's understand this more by an example. An example, this would be more like an activity, and I saw this in NCRT book and I found it very interesting, so I would like to share it with you guys. So consider, so we have an empty bottle, right? And another thing I would like you guys to do is like make sure the cap is completely sealed, airtight, so no air or water or any kind of fluid can go inside in it. Now let's imagine, okay, I'm going to use a different color here. So let's imagine we have a bucket, okay, and then which is filled with the water, okay. Okay, so it's like half, let's say it's half filled with water, okay. Now if I am trying, let's try to immerse this plastic bottle inside the water, and you will find it very hard because you will see that the plastic bottle doesn't want to go inside the water unless you apply a lot of force. You need to apply a lot of force on the plastic bottle to make it go inside the water. Okay, now so far, based on all we have learned so far, is the plastic bottle has a weight. Okay, and that is because of the gravity. So the weight of the plastic bottle is acting, I'm gonna use a red color here, so the weight of the plastic bottle is acting downwards. Okay, now if the weight of the plastic bottle is acting downwards and I'm applying some force which is also in the downward direction, then why the plastic bottle is not sinking? There must be, and the only explanation to this is like there must be some kind of force from the water which is pushing this plastic bottle upwards. Let's say this is B. Okay, so if the plastic bottle is not going inside the water, the B force must be greater than combination of the weight of the bottle plus the force you are applying. Okay, so and if I apply my force, F becomes very large, then there must be something is happening which is making that W plus F greater than B after I apply a lot of force. So F is increasing quite a bit, and that's why and then probably that's time the plastic bottle is going inside the water. So the B force, this is called buoyancy. Okay, this buoyancy force, it's acting on this plastic bottle against the motion I'm trying to do here, pushing the bottle downwards. It's acting so that it's pushing the bottle upwards, in the opposite direction. So this buoyancy is telling that I don't want the bottle to go inside the water, but the weight is telling me it has to go inside the water. So there is a balance there. If both W plus F is greater than buoyancy force, then I can immerse the bottle in the water. If not, then bottle will not go inside the water. Okay, so this B is buoyancy force. Okay, so in this particular activity, what we learned is like all the fluids. Now we looked at just water, but not only the water, all the fluids will exert this buoyancy force on an object. So far we have learned like there is a mysterious force, the buoyancy force, which is acting on this water bottle. Now I'm gonna look at another activity to give you a little bit of hint more about this buoyancy force. So let's consider we have a nail. So I'm gonna use a red for nail here. Okay, and we have a cork. So let's say the cork is here. So and then we have a river. So now if I put this nail and the cork on the water, what happens? So you will see like after some time, and if this is, let's say, the bottom of the river and this is the top of the river, after some time you will see the nail is on the bottom and the cork is actually floating on the river, on the surface. So now why is that? right? Means why a river where the nail is in the bottom of the river but the cork is not. Now one thing I forgot to tell you, let's assume both the nail and the cork is same mass, so let's consider both are 1 gram. Okay, so if even though they both are of the same mass, you will see nail is actually at the bottom of the river and cork is not. Okay, we know both of them have the same gravitational force because they have same mass, and acceleration due to gravity is going to be same for both nail and the cork. So weight for both is 1 gram into 9.8 meter per second square, right? So weight is same in both the case. Then why one is sinking, one is not? I'm going to give you a little hint here. Let's see, the density of the nail is dN, density of the cork is dC, and density of the river is dW, which is water, right? So we all know the density of the nail is going to be much higher than density of the water, and density of the cork is going to be much lower than the density of the water. So from the experiment we did, the nail was sinking and cork is floating. Okay, so this hint will give you an answer that as long as the density of an object is greater than the density of the fluid, okay, then the object will sink. If the density of the object is less than the density of the fluid, then the object will float. Okay, I hope this was clear. Okay, so why density is affecting so much? Let's try to understand that. So somehow we talked about in the previous activity when we looked at the bottle example, and we were trying to sink the bottle and we could not because it takes a lot more force to do that. We know there is some kind of mysterious buoyancy force was acting right on the bottle. Now here we learned that the density of an object is important. Okay, so somehow, now this is going to be another clue here. So somehow that buoyancy force is connected to the density. Okay, so the density has some effect on the buoyancy force. So that's another clue here. So we'll slowly learn more clues and try to come up with expression of the buoyancy force. Okay, and the expression for this buoyancy force and like what other factors affect this force and how we can calculate this force, what's the mystery behind nail sinking and cork not, all that, the expression we will learn in the next lecture. Okay.